right? All right, so I'm going to start from trying to understand K0. It's going to be a review of projective modules and vector bundles at first. Just trying to understand where to see comments. Oh, shoot. All right, this should fix it. All right, now I have a chat. Still live. All right, we can start learning. Okay. All right. Okay. Seems like everything is in order now, so we can start. So first of all, we're going to talk about free modules and projective modules. But first of all, this part I already read is Bible talks about invariant basis number, which is an important property where basically the dimension or the rank of a free module is well defined. So Rm and Rn not isomorphic when M is not N. And of course, if you can extend biscalars to a field, then because the tensor product respects direct sums, you can show that you get, and because dimension in vector space is well defined, you get a dimension. Because, yeah, dimension is independent of choice of basis. Okay. So, our choice to use right modules. Oh yeah, they use right modules, which is disgusting. Like, I don't know why anyone would ever not use left modules. But anyway, yeah. So they use right modules. In particular, homomorphisms may be thought of as n by n matrices with entries in R, acting on the column vectors in Rn by matrix multiplication. You write M and R for the ring of n by n matrices. This is standard. And write GL and R for the group of invertible n by n matrices. And of course, we have R times group of units. For any finite dimensional algebra R over a field or division ring, F has an invariant basis property because the rank of a free R module is an M of it. The rank is the dimension of F M over the dimension of R. Oh yeah, this is sort of the tower law with algebras. If you have a module over some algebra over a field, and then you have over that field you have, or I feel like maybe this should be the dimension over R. But no, wait, sorry, that's not well defined. Yeah, I'm not sure why this is true. I want to try and convince myself why this is true. So, if we have a free R module, then yeah, so basically we have so if we have a free R module, then we have some sort of basis, and so yeah, I have some basis for M over R, and then I can do the usual thing where you do in like tensor products, which I have a basis of R over F, and I can take all the products and I'll get a basis of R of M over F, which is going to be of the dimension of F, which when I divide by the dimension of R, I'm going to get the rank. Yeah, okay. So for a simple Artinian ring, we can say even more. Yeah, so my beloved Wedderburn theorem says that R is M and F for some N and F. F here should be a division ring. And that every right R module is a direct sum of copies of the projective R module phi, consisting of row vectors over F of length n. Yeah, this is all very basic Wedderburn-Artin theory, and the number of copies is an invariant called the length. Oh, I didn't know that it coincides. Okay, it makes sense because it's a semi-simple module. The length is also the dimension over n, since the dimension over F is equal to n. In this case, we also have that the rank is length over n, which is the dimension over n squared. Okay, yeah, the length is dimension over n. Yeah, there are non-commutative rings which do not satisfy the IBP. Yeah, the examples are actually pretty awful for rings that don't satisfy the IBP, but they do exist. Do I actually think I'm not capturing, or am I? Yeah, I don't think the video is capturing the entire screen. At least on YouTube, I don't think you can see the entire screen. Okay. So, yeah, rank is not invariant of free modules over these rings, and infinite matrices are one of these examples. Yeah, it's a pretty nasty. So an R module is called stably free if you add enough copies of R to it, it becomes a free module. So, like, in some sort of limiting sense, it is a free module. Like, I don't know why anyone would ever not use left modules. Alright, okay. So, if R satisfies IBP, then the rank of a stably free module is easily seen to be independent of the choice of M and N. Yeah. So this is going to be, so I know that K0, the K-theory of which is basically projective modules growth in a group. So these stably free modules are going to be important because they're like, yeah, they're going to be important. So the kernel of any surjective matrix, M by n, is a stably free module because a lift of a basis of Rm yields a decomposition. Yeah, okay, so if I have a map from Rn to Rm, then these are free modules, of course, so this, oh, and it's surjective, so there's a section, and then that section is going to give, yeah, so if you have a basis for Rm, you lift it to a basis to a linearly independent set of Rn, and then you complete it with the basis of the kernel. Sorry, we don't complete it with the basis of the kernel. The kernel might not be a free module, actually. It's not true that being a free module is always hereditary. But you can show that it is going to be a direct sum with the kernel because it's a section and it's isomorphic to the image. This is like basic splitting lemma stuff. If you have a surjective map and then you have a section, then it's the kernel direct sum with the image, yeah. This raises the question, when a stably free module is free? Over some rings, every stably free module is free. Fields, obviously everything is free. Z and matrix rings are classical cases, but in the general case, it's not even so, even if R is commutative. So let's see some examples. The most important special case, at least for inductive purposes, is when m equals 1. So you just add one copy of R. In this case, sigma is a row vector, and we call sigma a unimodular row. Sigma is in this here, yeah, the kernel of a stably free. So P here is going to be the kernel of a matrix because you can take Rn and project onto this, and you get a matrix with kernel P. And then conversely, this matrix is this matrix gives a stably free module. So if you have a stably free module, then basically the row vector here is going to be the projection of Rn onto this R component. So we call sigma unimodular row. It's not hard to see that the following conditions on a sequence of elements are equivalent. Okay, so sigma is a unimodular row. Rn is, then P is the kernel of R, and the projection Rn to R is sigma. Yeah, obviously, R is equal to R1 times R plus to Rn times R. Okay, so why is this true? If sigma is a unimodular row, then oh yeah, the elements in the projection. So this row vector means that when you take an element of Rn, take that. So this means that Rn to R is surjective. Yes, and then that means that the kernel is going to give you the stably free thing, and then this is the same thing because, of course, if you can generate, because this is R linear, if you can generate one, you can generate everything. So these are easily seen to be equivalent. So great. So that's great. Now, if Rn is isomorphic to P direct sum of R with P free, then a basis of P would yield a new basis for Rn, and hence an invertible matrix whose first row is the unimodular row corresponding to P. This gives us a general criterion. P is a free module if and only if the corresponding unimodular row may be completed to an invertible matrix. Because if you could complete it to an invertible matrix, then those vectors would have to be independent with the unimodular row, which is the unimodular row is basically the vector that spans this copy of R. So they would have to be independent with it, and therefore would give a basis of P. Or at least, I think this is like up to isomorphism. but yeah, it doesn't matter because if you find another complement which is free, then both of them are isomorphic to quotienting by R, and then it's isomorphic to a free module, so it's actually free itself. So, okay, so if you can complete it, then you get that P is free. Invertible matrix is in GLN R if R satisfies the IVP. Not sure why it needs to satisfy IBP here. Like GLN means invertible matrices. I guess. I'm not sure. When R is commutative, every unimodular row of length 2 may be completed. So yeah, so if you have R1S1 plus R2S2, then the desired matrix is this, because then this is going to be independent. These are going to be independent. Why is that? Let's see. If you have R1 and R2, you have minus S2 and S1. Try and give a linear combination. I think you can multiply by S1 and S2 and get some sort of sum. I'm actually not sure why this would be linearly independent. Oh, I'm stupid. The determinant is non-zero. The determinant is invertible, actually. So it's an invertible matrix. Yeah, obviously. Of course. So R squared is R plus P, implies that P is isomorphic to R. Yes. In section 3, we will obtain a stronger result. Every stably free module of rank 1 is free. But that R is commutative is crucial. In example 1.6, we give an example of a unimodular row of length 2 cannot be completed over some non-commutative Hell ring. Yeah, okay, so let me just think for a second. So let me just think for a second if so if you can complete it to basis, you get a different complement. The unimodular row is actually like, okay, if you have the projection onto the R component, I want to see if the unimodular row is really the row R1 up to Rn. I think that is true, that this copy of R is spanned by it. So, and the isomorphism is given by just multiplying the column vector okay, no, I feel like this is a really silly thing, but I'm getting stuck on the linear algebra. So it's a unimodular row, so the projection from Rn to R. So this is given by a okay, so if you have a basis of P, then this is implying that the vector R1 to Rn indeed represents the unimodular row, which I'm not quite sure about now. I think it's like a dual vector thing. Yeah, the projection is multiplication by a row vector. So kernel of this thing is all the elements that. Okay. I'm not sure why this gives a new basis for Rn, whose first row is the unimodular row. It's not sure why this being the representing vector implies that. Yeah. I think this is not going to be that important, as long as I understand that the criterion is true. The why exactly it is true is not that important, but I still want to try and understand it, but I feel like I'm getting stuck on it. The map R into R that corresponds to P is going to be just taking a row vector, multiplying it by the column vector. So if you want a map back to Rn, then which is going to be a section. So if you project and then if you come back and then project, you want to get the identity. So if you have an element of R, how do we build a section? So we know that 1 is equal to R1 times S1 for some Si. So we can have R be R times that. No, I don't think that works. I'm going to send that R to just... Yeah, okay, so I'm going to send R to R1 times S1 plus R1 times S, and then the second element is going to be R1 times S2, and so on. So it's going to be, sorry, R times S1, R times S2. So it's going to be actually the vector of the SIs, because it's going to be sent to 1. That the image of the projection is going to be 1. So it's actually going to be the SIs, but this is actually symmetric in the SIs and the RIs. So the SIs are also a unimodular row, and you still get the thing where it has to be independent with everything else. Yeah, so moving on. I don't actually care about this stuff, so let's just move on to Bass cancellation theorem for stably free modules. Let you have a commutative Noetherian ring, so every non-empty set of ideals has a maximal element. Curl dimension P means that there's no chains of more than P prime ideals. And every stably free R module of rank more than D is a free module. Equivalently, every unimodular row of length n greater than or equal to D plus 2 may be completed to an invertible matrix. Why D plus 2? Oh, because it's... Oh, okay, yeah. That's right. Study of stably free modules has a rich history. Yeah, Lamb's book. So Lamb's books are actually really good. Yeah, so this stably free nice criterion bunch of exercises, which probably not going to do most of them because I'm trying to go through this pretty quick, but we'll see in the future. So now we get to projective modules. Of course, I know the definition, but so an R module is called projective if it's a summand of a free module. It's equivalent to saying, of course, this is not the same as stably free because Q doesn't have to be free here. This is equivalent to saying that P satisfies the lifting condition. So for every surjection of R modules and every map P, there exists a map making this diagram commute. So to see that these are equivalent, they actually prove it here. It's nice. It's also a nice little exercise. So first of all, free modules satisfy this lifting property. Free modules are projective because with this lifting property, why are free modules projective? Because say P here was free, then I could take basically, so I want a map F such that G is equivalent to SS. So take a basis of P, look at the images on the G, lift them to images here, and then choose a map that maps the basis elements to the lifts, and then you get the commutative diagram. So free modules satisfy this property. So F is determined by lifting the image of basis, like I said. To see that all projective modules satisfy the lifting property, extend G to a map from free module P plus Q to N, and lift that. So, yeah, so you just extend by just taking the projection, and then you just do the property on that, and you can show that actually when you restrict to P, you get the lifting diagram. Yeah, extend G to a map to N, lift that, and if P has the lifting property, you choose a surjection, and then P has a section, and by splitting you get the direct sum. P is projective, and P is generated by N elements, if and only if there is decomposition, plus Q is Rn. So the generators give a surjection, let's use the decomposition. So yeah, this, and if there is such a decomposition, then the surjection gives the generators. So there's an if, as the mathematicians like to say. Actually, no one says that, but we have a little fun here. Okay, so we'll focus most of our attention on finitely generated projective modules. The morphisms are module maps, of course. Since the direct sums of projectives is projective, the characterization of being a summand of a free module makes that very clear. Then here is an additive category. We may regard P. So let me just remember what an additive category is defined as. So an additive category is a pre-additive with byproducts, and pre-additive category just means that there is an addition operation, which there is in all module categories. So you get that PR is an additive category. We regard P as a functor in rings, since yeah, you can just get a map by extension by scalars. And so Y is extension by scalars, and not sure what P prime is supposed to be here, but never mind. So there is a nice characterization that P is projective if and only if the Hom functor is exact. This is equivalent by abstract nonsense to the lifting property, and so you can show that because free modules are projective and S is a free module over itself, you can show that actually the Hom, if you put this by Hom tensor injunction, again abstract nonsense, this is going to give you a composition of exact functors, which is going to be exact. So this is a well-defined map, but I still don't know what P prime here is there. So if P is projective, okay, just getting ahead of myself. So if P is projective, then P is an exact, so the tensor product is exact, and the Hom functor is exact. The reason that the tensor product is exact is not. So I think this is why you want right modules, because then you can put this in the first coordinate. The fact that the tensor functor is exact is not trivial. You can show that pretty easily if you know about the definition of derived functors, but that's maybe kind of cheating. But showing it directly is not that fun, but you can use the lifting property to show it, I'm pretty sure. So, any exact sequence yields exact sequences. Actually, let's check projective module tensor is exact. So this is saying that projective. So this is saying that basically projective modules are flat. Denote the injection, ejection. Since this is ejective, projectivity of M3 gives us this map. So yeah, the splitting lemma. Okay, so the splitting lemma gives a left inverse to. So if alpha is the map from M1 to M2, then and beta is the surjection, then he's saying that this should be from M3 to M2. There's something wrong with this answer. I'm not sure if you're seeing this properly. Yeah, there's something wrong with this answer. It's saying that the map is split. Map beta is split, but this gives a map from M3 to M2, not M2 to M1. This is a retraction of beta. I'm not sure what. Okay. Okay, so projective module is flat. So first of all, is suppose you have a left. Yeah, you only need to check left exact sequences because tensor always preserves the right exact part. In P is projective, we have that. Okay, it's not very nice. So maybe, okay, so projective modules are flat because I think you can sum up to free modules. Showing free modules are flat is very easy because free modules, showing something with free modules is just taking direct sums, and then you can show that because you lifted this up to, you can show that actually every direct summand of a flat module is flat because if you have splitting into a direct sum, you get two exact sequences that you take their direct sum, and then each one of them in particular is going to be exact. So yeah, so that's one way of showing that projective modules are flat, is you just do the tensor sequence, and then you do that with the other direct sum, and then you take direct sums, and you get something with free modules, which is going to be. Wait, does that work? No, sorry. I think you first take you first tensor with the free module, and then you take you do the direct sum decomposition, and that gives you basically two parallel short exact sequences that you add together, because a direct sum of short exact sequences is again short exact. Like a direct sum of sequences is short exact if only if each summand is short exact, because the maps basically don't interact with each other. It's because kernels and images preserve direct sums. Yeah, so kernels and images preserve direct sums. That's even true in the case of like a abelian category. It's like the images kernel of a direct sum is the direct sum of the kernels, because basically being zero is a pointwise condition, and same as being in the image. So, of course, free modules and stably free modules are projective because the summands of free modules. Idempotents are useful, but I already know stuff about them. If R is a PID, then all projective modules are free. Right, there's a nice theorem it follows from the structure theorem, because even for infinitely generated projectives, interesting. I wonder how you can do that, because the structure theorem is usually for finitely generated modules over a PID. Okay, interesting. So not many other classes of rings have all finitely generated projective modules free. Hemisphere of Quillen and Suslin says if R is a polynomial ring or a Laurent polynomial ring over a field or a PID, then all projective modules are free. Okay, that's nice. Okay, so there's this lemma. If R is a local ring, then every finitely generated projective R module is free. I think I proved, okay, so maybe not this part where the dimension is actually this, but I think I proved this. Did they prove it? Oh, okay, they prove it here. Nice. I think I did this as an exercise in ComAlg. So we are using commute. Okay, sorry, we're defining. Okay, so we're defining local ring for not necessarily commutative rings. I did this for commutative rings, but yeah. Okay. We observe that every element is invertible in R mod M is a unit of R, i.e. UV equals VU. So this is by locality, basically, because if you're invertible in R mod M, that means you're non-zero, that means you're outside. That means you don't live in R minus M, which means you're a unit. So yeah, multiplying by a representative for the inverse, we may assume that U is in 1 plus M. Because once we multiply by a representative for the inverse, then we get 1 plus M, yeah. Since M is the Jacobson radical, any element of 1 plus M must be a unit. So that's also not another way to prove it, but I think mine is a little bit simpler. That just because if you're invertible in R mod M, then you're invertible in then you're outside of the maximal ideal. But yeah, that's another way, I guess, because basically the Jacobson radical is all of the elements such that 1 minus that element is a unit. So if you do, what is the defining property of the Jacobson radical that they're using here? Here, okay, is JR is all superfluous. Yeah, quasi-regular. The Jacobson radical has some characterization with, okay, its total elements such that, in fact, y is the Jacobson radical if and only if 1 plus xy is invertible. So I'm not sure what they're appealing to here. M is the Jacobson radical, so it's the collection of all, it's in the intersection of all maximal ideals. So any element of form 1 minus M must be a unit. Yeah, because, okay, so basically any element of 1 plus M must be a unit because if you do 1 minus that thing, you go into the Jacobson radical. And things in the Jacobson radical. So basically the element is inside. If it was in a unit, it would also be in the Jacobson radical. But then that would mean that the Jacobson radical is the entire ring, which is impossible since there is a maximal ideal. I don't know why they needed to phrase it like that, though. Okay, suppose that P plus Q is Rn, so we're on a projective as vector spaces over R mod M. P mod MP is FP and Q mod MQ is FQ for some P and Q. Yeah, because we're assuming finitely generated. So Q should also be finitely generated. I think you can always choose the complement to be finitely generated. Yeah. Okay, so you can always choose like n to be finitely generated, like Rn, you can choose n to be finite by taking generators of p, like taking the number of generators of p and doing the surjection, and then the kernel is going to be that, but the kernel is not necessarily finitely generated. Is it? Submodule of finitely generated module. Yeah, so submodule finitely generated modules need not be finitely generated. Maybe over a local ring they are? Over a local ring. Let's see. If a finite module over an Arthurian local ring, support only the maximum ideal. Okay, that's not the question that I wanted to ask. Still not sure what they're appealing to here. It's like, oh, okay. I'm being silly. It's because this quotienting preserves direct sums, and then P is finally generated, Rn is finally generated, Q must be finally generated because in vector spaces dimension acts very nicely. Or, I mean, it could be a division ring, but vector spaces over division rings are basically vector spaces. Okay, so P is, so choose a basis, so choose lifts of bases, and the EI and EJ determine a homomorphism from Rn to Rn, which may be represented by a square matrix whose reduction is invertible because that gives basically a change of basis matrix from this new basis to the standard basis. But every such matrix is invertible over R by an exercise. So if you're invertible, quotient by a maximal ideal, apparently you're invertible. Therefore, this is a basis for P plus Q, and therefore it follows that P is free on this basis. So, oh yeah, so this means that this is a basis because the matrix is invertible. So the change of basis matrix is invertible, so that means that it's basis. Yeah, okay, cool. Even infinite generated projective R modules are free when R is local. Interesting. Still not okay. I guess I'll I'm not sure when you wrote that comment, Ron. Okay, let's see. Even infinite, so if P is a prime ideal of a commutative ring and P is a projective R module, then the localization is free. So yeah, so projective modules are locally free. This is also an exercise I did in commutative algebra. Moreover, there is S in R minus P such that the localization of P away from S is free. Right. This is this ass exercise that I spent way too much time on, which is like P is projective if and only if P is locally free, if and only if there is like a set of elements that generate the unit ideal such that the localization in each of those elements is free. So this is kind of similar. Okay, let's see. So, in particular, for every prime ideal not containing S. Oh, right, because if you localize, because it doesn't contain S, if you localize twice, that's the same thing as localizing the first time. That's a big point of that theorem, actually, of like proving that, is that localizing twice is the same as localizing the first time. If you localize like part of a set and then you localize the rest of it. P plus Q is equal to Rm, then yeah, so P is a finitely generated projective module, but Rp is a local ring, so Pp is free. Now every element of Pp form P over S for some P and some S in R minus P. By clearing denominators, we can find an R module homomorphism which becomes an isomorphism upon localizing at P. So it's free now. Every element of PP is of this form. So we can take an R-module homomorphism, which when you localize it, P becomes an isomorphism. Because, yeah, you can take a basis and you can multiply it by denominators. And then you can just map to that basis. And then you can get back your basis by it because, well, scalar multiples of a basis still give a basis, which becomes an isomorphism. So the co-kernel is finitely generated. So this is like Nakayama. As the co-kernel is finally generated, which vanishes upon localization. The co-kernel is finitely generated because trying to think. Okay, this homomorphism. Co-kernel is finitely generated because P is, of course, and it is also annihilated by S. Yeah, because it's finally generated, you can find a single element that annihilates the entire module, just because there's elements that annihilate every generator. So for this S, this map is onto, but since P1 of S is projective, then there is a splitting. But when you localize to P, you get 0, but M is annihilated by some T, so you take this ST, and then you annihilate the direct sum, and then you get that. This map is onto. Why is this map onto? Because, the co-kernel is annihilated. You localize. Right. That means that the map is onto. Okay, very cool. So this shows that there's this thing, and suppose there is a ring homomorphism from R to a field. That finishes the proof. Yes, very cool. Nice proof. Like localizing killing things is a fun thing. Yeah, and is this quotient, then it's finally generated, and M sub P is 0. Yeah, okay. Up here, okay. Because PP is free, it has a basis, then just clear denominators of that basis, and that's still a basis. Okay. Coolio. Recall that so suppose there is a ring homomorphism to a field. If M is a module, then the rank of M is at F is this dimension. The rank depends upon F, obviously, because different embeddings are going to give you different ranks. So if you have a product of fields or division rings, and M is one of the factors, then if you take, one map from R to F, which projects at the first factor, you're going to get 0, and you're going to get 1, and at the second factor, you're going to get 0. When as commutative, every such homomorphism factors through the residue field at P with some prime ideal P, so we consider rank N as a function on the set spec R of prime ideals. It factors through residue field because when R is commutative, then you have a map from a ring to a field. It has to be injective. Or rather, sorry, the kernel is going to be a prime ideal. Then you have the projection map, and then, of course, if you take the field of fractions, that's still going to give you a map. So yeah, okay, cool. Still weird that it depends on f. It feels like it shouldn't, but it obviously does, because the way you extend scales changes things. Recall that Eck has the natural structure of a topological space, but the basic opens are ds, which is spec of 1 over s. Okay. So now the rank of a finally generated R module at a prime ideal P is just the dimension over the residue field. Rank P is the minimal number of generators of MP, right? Because Nakayama tells you that if this is true, then MP is generated by rank P elements. Right, that is one of the formulations of Nakayama's lemma. Let's see. Nakayama. So yeah, if M is finally generated and the images of elements generate, then they generate, yeah. And of course, it's the minimal number. If you have a smaller number of generators, then they would also generate the quotient, which is not possible, obviously. So if P is a finally generated projective R module, okay, and so if P is a finally generated projective R module, then the rank is continuous to the discrete topological space N. We'll view rank as an element of the two sets. Continuous map from spec R to N and Z, respectively. It's not trivial, I think, but I don't understand what projectivity has to do with it. Maybe the fact that a projective module is locally free, but I'm not sure. Okay. P is constant rank if the rank is independent of P. Of course, spec R is topologically connected, every continuous function must be constant, so every finally generated R module has constant rank. For example, if R is an integral domain, spec R is connected, every finally generated projective R module has constant rank, which is equal to the dimension over the field of fractions, because everything factors through the field of fractions. You just get like partial, you get stuff where you, in an integral domain, it's just, in the field of fractions, you just take a subring with less inverses. So everything is just localizing twice. So you get that it's constant. So conversely, if a projective P has constant rank, it is finally generated. Okay, this is exercises. If M is not projective, rank M need not be a continuous function. So, yeah, just to make sure I understand, this example shows that this dimension depends on F, but for now it is commutative. Homomorphism factors always, so you can think of the rank like that. Again, it factors because it factors to the inverse, and then you can localize. Universal property of localization is what lets you do this, actually. So basically, the universal property of localization tells you the following thing. If you have, so you have the localization map, which, so you have a map basically from R to the quotient, you have the localization map, and then you have a map from R to your field, and of course it maps every element that's not in the kernel to a unit. So in particular, if you take the first isomorphism theorem thing, then every element in the quotient gets mapped to a unit. So there is a map from the, how do you call it, from the localization. So that's how we get this factoring through thing. Okay. Now I don't care about this stuff. So Bass-Serre cancellation, this is interesting. So let R be commutative Noetherian of full dimension D, and let P be projective of constant rank N. Said that if P is P0 plus Rn minus D for P0 projective constant, said that this is always true. If P is stably isomorphic to P prime, then P is isomorphic to P prime. And for all M and M prime, if P equals M, stably isomorphic to M prime, then it's isomorphic to it. Interesting. Okay, so there's a way to turn stable isomorphism into just straight up isomorphism. Okay. If P is a projective module whose rank is not constant, then P is a product of projective modules over these rings, I guess. Okay. Open patching data. So, not sure what he means by patching here. I think Milner has some work in patching, but I am working on field patching right now, which is similar to other concepts of patching that are more historic, but a little bit different. Sometimes useful to be able to build projective modules by patching free modules. Yeah. So the following data suffices. Suppose that S1 and SR form a unimodular row, then spec R is covered by the open sets. So let's think about why, because, yeah, every prime ideal can't contain all of them, so it is contained in one of these DSIs. And suppose we're given Gij in this GLN with Gi equals 1, so 1 on the diagonal, and there's this cocycle condition. Then P, which is this module, is a finitely generated projective module, because each, when you localize it 1 over Si, you get, when you localize it 1 over Si, you get free module. So when you localize that by, it's 2.4. 2.4 is this lemma, which I skipped. So null module is locally free for every prime ideal, and then the C module. So finally generated projective module is the same thing as locally free. So yeah, so this basically tells us that this P is going to be locally free. And this Gij, Xj equals Xi in R. Okay. I'm not sure why you need to do this patching, but I'm not going to get into it. Oh, and this is Milner patching. Yes, but I don't think I need to get into this right now. Yeah, Milner patching. This is different from the stuff that I do in field patching, though. Okay. The Algebraic swindle. This is a cute example. But I want to get into vector bundles, and then we're going to do some K-0. Card group for computer different. Let's see this again. Okay, so card group, then topological vector bundles, and then algebraic vector bundles, and then we get into K-0. So I think I'm going to stop here. Next time I'm going to try and get through all of these, get to do K-0 at least up to here, and then I'm going to try and read about how K-0 interacts with field patching, because like my project that I'm doing right now, I want to figure out how K-theory interacts with this patching over fields. So I need to first understand K-theory, and then I need to understand patching. So that's what I'm going to do next after I understand K-0 at least, and then need to try and see if I can show it for K1 as well, which might be a little bit harder. So that's going to be it for today. Had a pretty productive time, I think. Thanks for anyone who tuned in. Thanks, Ron. Uh,